Okay, this session is only related to the guys who are doing naval arc and marine. We will be looking at pipeline problems, a fluid flow, and how to get the best fluid flow, what's the power and everything. Now, when we talk about the pipeline problems, we have a look at the Bernoulli's equation. The Bernoulli's equation states that all the energies are going to be constant. Energy at the inlet should be same as energy at the outlet. And then if there are any losses, we just add the losses on that side. Yep. So shock loss, friction loss, heat loss, any other. Now the standard shock loss as entry and exit occurs only when the entry or exit is sharp, the flow is flow is out of into the reservoir. So the conditions are those of sudden contraction or sudden enlargement, which mean the diameter is going to change, the velocity is going to change, though the flow rate is constant. Then we use a formula known as Darcy's formula. Darcy's formula is given by that one. The head flow is 4, Froude's number L divided by the diameter multiplied by the velocity divided by the 2g. We will discuss that one in detail. Okay, so if we go to the next slide, please. Now we got the Darcy formula. If the pipes are in series, the friction loss, we add the friction loss. So if there is a one pipe and I know the friction loss is provided, and I got another one, so I can add the friction loss. Now in case the pipes are in parallel, the energy equation, we need to write down energy equations for each and every branch. And we need to actually have a look at the energy lost per rate. If we go to the next one, please. Now, so today we are going to have a look at two main things. Calculate the discharge to the pipe of known diameters, known geometry, length and diameter, and calculate the shock losses. The second is apply the energy equations on a parallel one. So if we got time, we go to the second one as well. Next slide. Now let's say I got a problem, a pipeline connecting two reservoirs having difference of level of 6 meter in 720 meter long. So this is first reservoir. Yeah, the top of this reservoir and the top of this reservoir. The datum difference is 6 meter, height 6 meter, and it's over a period of 720 meter long. Yeah, and at a point it goes up 3 meter from the upper level of this reservoir. So it goes up 3 meter here, upper level of this one. Okay. At a distance of 240 from the entrance before falling to the low reservoir. So distance of 240. So A to C, that distance is 240, and the total length is 720. So I can find that distance as well. Yeah. Okay. If the pipe is 1.2 meter in dia, same pipe is here, so diameter is same. If the pipe diameter is 1.2 meter in dia and the frictional coefficient F is 0.01, so frictional coefficient F is given 0.01, what will be the discharge? Now to find the discharge, we know we have a formula, Q equals to VA. Sorry, control. That was slide number, that one. Okay, so Q equals to VA, where V is the velocity, A is the diameter. Now the A is already given. To find that one, the missing thing is this velocity is the missing bit. So I need to find out this velocity. Okay, so let's see how we work with that problem. Now if you go to the next slide, please. Now in this question, there are no information at that exit or entry of the pipe is sharp, or there is a shock losses. It's not provided. If it's not provided, we assume they are 0. They will provide you with that categories. But if it's not as a category is provided, we assume that's 0. Okay. So we will apply the Bernoulli's equation at the entrance, and we will apply the Bernoulli equation at the exit. So we'll apply Bernoulli's equation, and we will have a look at the velocities. Now, velocities at the point A and at the point B, which are the reservoir, its velocities there at the surface are 0. The pressure at the surface of the reservoir, no matter if I draw that one. So if this is reservoir 1, and then there is another reservoir here, and the water is transmitting like that, the velocity here is going to be, the velocity at that point is going to be like 0. Velocity at the surface is going to be 0. The atmospheric pressure, which is the pressure here exerted by atmosphere, it's going to be like atmospheric pressure. So let's have a look. Now, according to the Bernoulli's equation, we are going to take B as a datum level. B is the lowest level, yeah, of the second reservoir, as given in the slide number 5. The total energy, we need to find out the total energy at A should be equal to the total energy at B and friction losses. Now we're not taking shock losses because it doesn't say the pipe has a sharp bend. If the pipe has a sharp bend like that, then we take the shock losses, because here there will be a shock. Yeah. Okay. Now then we rewrite the Bernoulli's equation. H plus PA over W plus VA square over 2G equals 0. I will explain why 0. PB over W plus V square over 2G plus the frictional loss. Now at both sides, the PA and the PB, they both are same. The PA and the PB, atmospheric pressure. At the A and the B, the pressure is atmospheric, so I can just cross these things out. The velocities at A and velocities at B, they are equal as well. Yeah, so they are not, well, they are equal and they are also 0. They're not moving. So that can be adjusted for 0. So then I will have this thing disappear with that thing disappear with this thing, and the only thing you got left is H equals 4 FL V square over D2G. Now the value for the H, which was the height, is given as 6 meter. The F is 0.01. The length of the pipe is 720, and the diameter is 1.2. The value of the G we are going to take as 9.81 or 9.81. Yeah, 9.81, 9.8, both are okay. So we put these ones, and we will get a value. The missing bit here, the thing that we don't know is this V. We don't know the value for the V. You can either do that way, or you can straight away rearrange the equation. So if you want to find the V, if I rearrange the equation will become V equals to H times a D times a 2g divided by 4 FL square root. And if you put the values here straight away, that will give you 6. We need to just make sure everything is in SI unit. 1.2, 2 times 9.8 divided by 4 FO 0.01, and the length of the pipe is in meters, 720. And if we do that one, we will get a velocity. Once we got a velocity, the question is asking us to find out the discharge. The question is asking us to find the discharge. So Q equals to VA. Velocity we got from here, and the area is 1.2. The diameter is 1.2, so radius is 0.6. And that will give us the discharge flow in meters cube per. Now. Now, to find the pressure at C, we need to apply the Bernoulli's equation. Now, Bernoulli's equation is given by that. So we already got the Bernoulli's equation. Energies on both sides should be equal. Okay. Now, I need to find the pressure at C, which is the midpoint. That's what I need to find the pressure. The atmospheric pressure, where PA is the atmospheric pressure, H is 3 meter because in the middle, the pipe was 3 meter high. The F value is also 0.01. The value of the velocity of the pipe we got is 2.2 meters per second. That's meter per second, so if you correct that one. The diameter of the pipe is 1.2, and the length of the pipe up till the point C was 240 meters. So we put these values in, and we are trying to find out the pressure at the C, at point C. So we put the values in. Now, the value for the height, I'm just going to put that one. Pressure PA is the atmospheric pressure, so 0 over W, that's going to be 0. The velocity is 2.22, we find just a minute ago. 2g is 2 times 9.8, and that one, just leave it as Frod's number, up to you if you want to actually do that or however you want to do it. I have just taken the V over 2g common. So I got 1 here, 4 here, F here, L here, and D here. Just put all the values, and you will get an answer of the height of the water, minus 5.26 meter of a water. Now the pressure that's exerted by 5.26 meter of the water, we got another formula. The formula for the pressure is rho GH. So the rho is the density of the water, which is 1000, multiplied by the G, which is 9.81, and the height of the water is 5.26, yeah, or minus 5.26. Okay. When we put that one, we will get an answer as 51.6, yeah, kilonewtons or kilopascals. Yeah. Now, what about the negative? Because the height was negative, if we go to the slide number 5, please. Yeah. We can see over here, that's point C is here. That's the point C. That's where we're finding the pressure now. And you will see it's up the datum. It's not below the datum. So we take that as a negative value. Okay. So the pressure now will be the pressure will be in such a way that it will like to come down that direction towards the B. So we take that into consideration and we write that pressure as negative. So if you move back to 7, please. So you can see the pressure at C is negative 51. Okay. Okay, now let's have a look at another question where we got a water from a large reservoir. So the water from a large reservoir, which is here, is discharged to an atmosphere through a 100 millimeter dia pipe. So that's the pipe there. And the length of the pipe is 450 meter long. So the pipe is 450 meter long, this pipe. The entry from the reservoir to the pipe is sharp. So the entry is sharp. And the outlet is 12 meters below. So the outlet which is here is 12 meter below. So that outlet is 12 meter below. The value for the F is given 0.01. We need to find out the discharge. What is the discharge? Now we use the same formula for the head. The head is given as 12. So we write down, we apply the Bernoulli's equation to the point A, which is here, and to the point B, which is here. Now at A, the velocity is 0. It's not moving. The fluid is kind of not moving. It might be here, but this is the point A, and this is under atmospheric pressure. So if I want to find out the total energy at A, that should be equal to total energy at B plus the loss at entry plus the frictional losses due to the Darcy formula. So we write the equation H equals V square over 2G plus V square over 2G plus 4FL, the Darcy's formula, V square over 2G. So we just put that thing in and we put the formula. Now in this formula, the H value is 12, the F value is 0.1, the length is 450, the D is 100 millimeter. Make sure we convert that one, and we put that thing, and we will get a value for the V. Once we got the value for the velocity, which is 1.14 meter per second, we need to find the discharge. You can use that formula for discharge, or you can use that formula Q equals to V times A, where V is, we just figure out the value for the V, 1.14 multiplied by the A is pi r square. You can do pi r square, where R value, the value for the R, you can do is, the radius is here, that's the radius. So, oh, sorry, that's the diameter. So R is going to be 0.05 meters. And we put that one in, and we get the value for the Q. And that will give you the answer in meters cube per second. So that will be a meter cube per second. So the units here, make sure that's in meter cubes per second. They should be at 3. meters cube per second. Okay, let's have a look at if we got pipes in series. So now here you can see there is a pipe from B to C, and then there is a pipe, another pipe from C to D. They both have different diameters. A water is discharged from a reservoir which is here at atmosphere, so the pressure here is at atmosphere pressure, through a pipe 36 meters long. There is a sharp entrance here, and the diameter is 50 millimeter. So the total length of the pipe is 39 millimeter all the way from point B to D. Now it consists of two parts. Yeah, for the first one, the diameter is 50 millimeter for 15 meters. The pipe then enlarged suddenly to 75 millimeter in dia for the remainder of the length. Taking into account the loss of the head at the entry, at the enlargement, that's the enlargement. Taking into account the loss of head at the entry and at the enlargement, find the difference of level between the surface of the reservoir and the pipe exit, which will maintain a flow of this one. So they've given us a flow of 2.8 decimeter cube per second. The value for the F is 0.0048 for the 50 millimeter pipe, and for that pipe, which is the value is 0.0058. So they got us two values. Now if you draw that one, now first what we need to do is we need to actually, we are given the value of the Q, yeah, because on there they gave us the value for the Q. The Q value was given to us. Let me just move it a little bit bigger. Okay. So we have the value of the Q. We say Q equals to VA. That's the formula. Q equals to VA. So what I can do is I can use because the flow rate at the Q at the tiny pipe is same as a Q at the pipe with a higher or larger diameter. So I can use that equation to find the V because the area is given. So I can say like, okay, the easy way to that one is Q I'm using for the velocity one is equal to A1 V1. Yeah, I need to find the velocity one. So velocity one is going to be equal to V1 is equal to Q over A1. Now Q is given, which is 2.8 decimeter cube. Now we need to convert that into 2.8 instead of decimeter. We need to convert that into meters. So minus 3. Yeah, decimeter cube into meter is minus 3. And the area is going to be pi r square. And the value for the r for the first one is 25. Yeah, the value for the R1 is 25 millimeter. And if you put that one in, we will have the V1 straight away. Yeah, rather using that complicated way. Yeah. Okay, here they use pi d square over 4. Once we got the V1, we need to find out the V2. For the V2, same thing. V2 is going to be Q over A2. The Q value is exactly the same, 2.8 times 10 to the minus 3 because the same flow rate, pi r square, R2 square. And R2 is given as diameter is 75. Excuse me. So we do 75 divided by 2. That is 37.5 5 times 10 to the minus 3. Minus 3 because we want to do that into meters and meters. And we will have a velocity 2 there as well. So once we got the value for the first velocity and the second velocity, so we have this velocity here and we have that velocity here. After that, we will apply the Bernoulli's theorem to the part A and the D. Yep, so A was at the start and the D was at the very end of the reservoir. Now the atmosphere pressure PA and PD, they are the same. At A and D, the pressure is atmosphere pressure. And the velocity at A is also 0 because at that point it's a container on the top, the velocity is 0. So we use the formula total energy at A equals total energy at D plus a shock at B, friction losses in BC. BC is the first pipe with a diameter with a radius of 25 millimeter. Then the shock losses at C, there is another shock loss, and the friction losses in CD. So that's the equation. So if you write this one down, please. Okay, the question is asking us to find the height. So we are going to apply the Bernoulli's equation. Now this equation will be now in this form. H equals to the velocity at 2 over 2g plus v1 square over 2g, half of that one, and the Darcy formula here. And this is the difference between the velocity at 1 and velocity of 2 because of the losses, as we said earlier. Yeah. Okay, and then again the Froude's formula for the second bit of the pipe. Yeah. Now we're trying to find out the H. You can straight away, rather simplifying, rather going to this step or this step, what you can do is you can straight away start putting the value in the first one. We have the velocity 2. We have the velocity 1. We know what the value of the g and the g is. You know what the value of the f1 is. We know what the length 1 is. We know what the velocity 1 is. We know what the diameter 1 is. We know g is. We know the difference between velocity 1 and velocity 2. We can put the values. F2 for the second pipe, length 2 for the second pipe. And then we got the D2 2G. We just put that one, rather simplifying. You can skip these parts there. Straight away you do that one and it will give you the answer straight away. Yeah. So if you want to try just by putting the values at the first one and you will find an answer. Please. Okay. Now let's have a look at the uniform draw off. If the supply is uniform, how does it actually work in that case? Let's say we got a water main is 100 millimeter in dia and 4.8 kilometers long. Supplies are taken from it uniformly at 7.5 liters per hour per meter of its length. Find the greatest difference of head between the point of admission, the entrance to the main, and a point of supply when admission is at one end, B at the center of the main. So you want at one end and the center of the main. So that's what we need to figure out. The Froude's number, the F is 0.0, friction constant is 0.006. Okay. Now let's have a look. If we go to the second one, next slide, please. Okay. Oh no, one before. One before? That's the one? Okay. Now, let's have a look at that one. With continuous draw off, because there is a continuous drawn off along the pipeline, the velocity and the friction losses of the head per unit length will change from a point to point. Now, rather taking the full length, we consider short length and then we try to integrate it, because the same thing will happen across the length. So we have a formula. The initial formula was h equals to 4f L d v square over 2g. That was the original formula. Now, I've just taken a part of it, so instead of h, I'm going to call it delta h. So I just call it delta h, and rather using oops, sorry, my relative changes. 1 second. Yeah. So now what I'm going to do is I'm just going to call it delta and small h. The 4f is still, instead of the whole length, I'm just going to call it delta. That's the delta x over a d and v square over 2g. Yeah, so I will do that one. Where d is the diameter, okay, where d is a diameter, and let's assume that k is the drawn off per unit length, and q is the flow rate past the given point, and q1 is the total rate of input. So according to the law, we can straight away say the total input equals to total draw off. Q equals to 0 when x equals to L, when the total length, there is at the very end there is no drawn off, so that's going to be equal to 0. And Q1 is K times L, because in the question it says that's it's per unit length. So Q1 equals to KL. Now I want to find out the Q at other points. So I can say Q equals to K bracket L minus L x, because that will be the remaining of the length. The total length is L, and if I'm at length x, the remaining length is going to be L minus x. And the formula for the Q is V times the A. The formula for the Q is V times the A. So I got the Q here. I got Q. Instead of writing it Q, I can write V times the A, where A is the area, equals to K L minus x. And then to find the V, I need to do K L minus x divided by the area. Yeah. And now instead of area, you can put pi r square. If you want to do pi r square, just put pi r square in terms of area. The way they have done here is complicated. Go that way, make your life a lot easier. Okay. So instead of the value A, I can just put pi r square. Let's do that one here. So pi r square, yeah, where r is a radius. Okay, this will give me the velocity. Now I can copy this whole thing. I can copy this whole thing, and I can put that one in this formula. So if you go to the next slide, please. Okay, yeah, that one. Now I need to put that v square over there. So that will become delta, that's a delta, h equals 4fl over d. Okay, instead of d, just to make it easy, can I write 2r, because d is equal to 2r, multiply by v square over 2g. So the 2g remains here. I'm just going to copy the 2g on this side. So now v square. V square is that whole thing. V square is, to find the v square, I have to just square that whole thing. Yeah. So let's square that one. When I square this thing, that will become k square L minus x square divided by pi square, and that becomes a R4. Now I can simplify this thing. But remember, the formula I'm getting is in terms of radius, yeah, not diameter. So it's going to be a little bit different, that one. I can simplify that one. As in one go. This is 4, this is 2. So I can simplify that one as 2 on the top. Yeah. So the 4 and 2, they can cancel. F is a F. L is an L. This is R. This is R and R4. So that becomes a, oh, again, sorry, I made a tiny error. There is a 2 here, and there is a 2 here, and there is a 4. So they will cancel completely. So that will become just an FL. And the R and the R4 becomes a R5. The G remains as it is, the K square as it is, and L minus X square as it is. Now remember, we are using the value for the R now, rather the value for the radius. Okay. Okay. Let me just duplicate the slide. Now if you go to the next one, please. Okay. Now if we want to find out the H, what we can do is we just put the values, all the values in the calculator. Again, we are going to use the integration, and then we just actually do the whole thing. So now whatever we got in the previous slide, we need to integrate that bit. We need to integrate the bit in the previous slide, where we are going to, where we're going to assume the length at two different points, when x is 0 or when x is L. Then we will have that kind of equation which is here. When we apply the limits, these limits, we will come up with this equation here. Okay. Now, when we got these equations, we just put the value. So h equals, now this is in term of diameter, but it does not matter which way you want to use. F k square L cube over 6g pi square d5. And then we just put the values. Now 64 is given, F is 0.006, L is given, yeah. So L is per meter, we can figure it out at two different ends. Diameter is there. The issue is with this K. The K value in the question, it says 7.5 liters per hour per meter. So first we need to convert the liters into meters. So that will become a 7.5 liters into meter cube. So times 10 to the minus 3. Now it's per hour. So divided by an hour, we convert that into seconds. Yep. And that will become a meter cube per second per meter. Yeah. So that's the value we'll get. Now if you want to find the h, we put that value in and we will get an answer. But do not put the value of the L at that point, because L is different at every point. Once we got this value for the h is 2.87 times 10 to the minus 10 multiplied by L cube meters. So if I want to find the difference of head, yeah, when length is when input, if I put the length 4.8 times 10 to the 3 meters, yep, I can just put that value here, and that will give me the head value 31. If I put that value as 2.4 times 10 to the 3 meters, because these are the two values, we can actually find out. Yeah, because one was initially in the question, one was 4.8 kilometer. They say it was 4.8 kilometer long. So we can actually split that into 4.8, and we can say 4.8 kilometer is 4.8 times 10 to the 3. That will give us a head of 31. If you want to find in the middle, that's 2.4. We put that one, the head difference is 3.88 meters. Okay, if I pause. If we go to the next slide now, please. Improving flow. How do we improve the flow of the liquid? Let's do by using one of the numerical question. Now let's say we got an outlet from a water tank. The outlet from a water tank consists of a sharp edge entry to the horizontal of the pipe. The diameter of the pipe is given as 150 millimeter dia. The pipe is 30 meter long. It discharges to another through a valve, and there will be a loss at the valve as well. When fully opened, the valve causes a head loss of equivalent to this value, 1/4 V square over 2G. The pipe has a Darcy friction factor of 0.006. What are the limiting improvement per meter obtainable by replacing the abrupt entry, abrupt entry of the pipe, or by removal of the valve in terms of the increase in discharge, or if I just remove that valve at that point? What are the improvement I can do? Okay, if you go to next one, please. Now if we are trying to improve the flow, we need to actually find out the energy losses. So we look at the energy losses at the free surface. So total energy at the outlet plus the entry losses plus the friction losses plus the valve losses, they all should be equal. Now, so I got total energy losses. If I want to do the head, H equals V square over 2G plus HL1 HF because of the friction, and HL2. HL2 is after the value of the valve, at the loss at the valve. Okay. Now, if I say the flow remain the same, the pipe has the same diameter, so V should be equal to the V1. And if we are talking about abrupt entry, we got the Darcy's equation, H equals to 0.5 V1 square over 2G. Yeah, so that's the value we got. And if I want to do at the second one, another abrupt entry, so we need to half that one as well. Because every time you just do an abrupt entry, that's going to be half. So that's half of the half, which is quarter. Then we use a Darcy's equation, which is 4 FL V1 square over D2G. The 4 is a 4, the L value, F value is given, the L value is given as well, and the diameter is also given. Yeah, so we put that value. Now, the only thing I got is V1 square over 2G. 2G is there, but V1 square is the one that's missing. Okay. Now, if we go to the next one, please. Let me see if I can make it a little bit bigger. Yeah. Okay. Now, once we got everything in the V1 form, once I got everything in the H, I got the value of the HF. Now, I need to put it back into the first equation. The first equation was where we put like H equals to V square over 2G plus HL1 plus HF plus HL2. So I'm just going to put the value of the V in that equations, all that equations, the value for the HF in that equation. So I just put, if I just highlight that one, I just put that value here. Now everything in this question, if you look at that one, it's a V1 over 2G, V1 over 2G. That one is V1 square over 2G. That's something V1 square over 2G. That's V1 square over 2G, that one. I can just add them up straight away. Take the V1 over 2G constant, and this is 1 plus 0.5 plus 4.8 plus 0.28. That will give me 6.55. And I will get 6.55 V1 square over 2G. Now, in the question, I need to find out the, let's find out the V1. To find out if I make V1 the subject, I can do that one. So let me just write it down. I got the H equal 6.55 V1 square over 2G. So if I want to make V1 the subject, that's going to be H 2G comes here divided by 6.55. Yeah, and then I can square root all that bit. Yeah, and I will get this answer, that one. Now here, when you square root 6.55, it give you this answer 0.3906. Yeah, so it's up to you. You want to leave it like that, or you want to just do this next step, that next step if you want to do, up to you. Now then I got the flow rate after that one, flow rate, which is a Q1. Q1 equals to A times a V1, A1 V1. So A is, I can find out the A if I got the radius pi r square, I can do that one, and the V1 is this value. So this is the V1 value, that. Yeah, or you can just put this value in, up to you which one you want to use. Okay. Now, once you got that bit, if I just move this thing up, once you got that value, we just substitute back into the equation 1, and we're going to put the HL1 as 0 because there are no losses. So we put H equals all these values, we just put that in, and we will now this time, and before we got V1, now this time we got the V2 using the same technique. You can stop like at that point. Yeah, don't need to do that step. The next one, this step is up to you if you want to do, but we can do that one. Now the second discharge is going to be equal to A2V2, but it's the same pipe, so the area is same. Percentage increase. Now after that one, we're going to have a look at the percentage increase. To find the percentage increase of the discharge, it's Q2 minus Q1. It's Q2 minus Q1 over Q1 multiplied by 100%. So you can actually put the values. Yeah. Now these 2GH, 2GH, and the A cancel. So you can just take the other values, and that will give you a percentage of 0.47. Yeah. Okay. Now if the entry is abrupt but with the valve removed, we got 0.5 V cube. We got 0.5 V cube square over V3 square over 2G. Okay. Yeah. I'm just going to upload this video on YouTube.